Hi, I hope you're having a great day. Let's take a look at more transformations of functions. If you recall in the last section we talked about shifting or translations where we had a vertical or horizontal shift of a function. In this section we're going to look more at stretching functions, shrinking functions, and reflections of functions. Specifically, our objectives are to examine and understand the graph of a function y is equal to a times f of x. We're going to look at and understand the graph of y is equal to f of a times x. Examine and understand the graph of y is equal to negative f of x and y is equal to f of negative x. So understand the different changes. Remember with horizontal and vertical shifts, we were adding a number or subtracting a number to the function or to the inside of the function. And then we're going to perform a combination of changes. So let's look at, first of all, the graph of y is equal to a times f of x. And there are actually two cases that we have to consider. We have to consider when the values of a are larger than 1, and then when the values of a are less than 1 and still positive. So I've drawn for you here a graph of just a function y is equal to f of x. I could certainly have used one of the basic functions, but I was just trying to get a good picture of what happens when we multiply a function by a value. So on this particular function, if you want to look at the points that I have here, this function has the points 3, 2, goes for the origin 0, 0, and then the point negative 3, negative 2. And those points aren't really that important right now. I will come back and talk about those in a minute. But really what you're looking at is the overall effect of multiplying the function by some number. So in this first illustration, what I've done is looked at the graph of y is equal to 3 times f of x. Now notice this 3 is on the outside of the function. And we kind of talked about that in the last section. When it's on the outside of the function, what we expect to happen is that the y values will change in some way. So the x value is remaining the same, the y value is changed. Well, think about that. If we multiply our original point, that is the y value in the original point, by 3, what's going to happen? Well, as this graph illustrates, when we multiply by 3, we actually get the point 3, 6, because that original value of y was 2, but 2 times 3 is now 6. When the point 0, 0 goes through that transformation, that actually does not change, because when we multiply 0 by 3, we still get 0. And then when we multiply our other y value by 3, we get the point negative 3, negative 6. So here again, we had a y value of negative 2. We multiplied it by negative 3 to get negative 6. Okay? Now, what happens when we multiply the y value by 5? Well, basically the same thing. We're starting with this original basic function. Not really one of our basics, but here consider it a basic. We start with this original function, we multiply the function by 5, so we're really just multiplying the y value by 5, and you can see that we would come to the points 3, 10. Again, 0, 0 does not change through that transformation, and then negative 3, negative 10. So what's happening to this original function when it gets multiplied by some factor larger than 1? It's almost as if you're on the ends of that function, if you will, and you're stretching it, and you're stretching it vertically. So you're pulling it vertically upward. And we're going to define that specifically on the next slide, but the idea is you're going to get a vertical stretch. You're just pulling it up, stretching it up as far as you can. Think about a rubber band that you have, and if you stretch it upward, what's happening? It's getting skinnier and skinnier, so to speak, if you will. In other words, it's getting more and more vertical. Now, what happens if that factor is less than 1? So I have the same basic function or same original function that we just described, and now, in other words, these points were still 3, 2, 0, 0, and negative 3, negative 2. If I multiply the y values by 1/2, I'm going to get the points 3, 1, right, because 1/2 of 2 is 1. 0, 0 does not change. And then if I multiply negative 2 by 1/2, that gives me a negative 1. So do you notice it's having the opposite effect? Right, this one was stretching it upwards, getting more and more vertical. What's happening here? It's going down, right? It's kind of compressing the graph. What if I multiply it by 1/4? Well, that's kind of hard to see here, but 1/4 of 2 is 1/2. 0, 0 is still there, and then negative 3, negative 1/2. So it's even getting compressed further. So what we have here, when the factor is larger than 1, this is called a vertical stretch. When the factor is less than 1, it's called a vertical shrink. And I have that written out for you here. The graph of y is equal to a times f of x is a vertical stretch of f of x by a factor of a if a is larger than 1. It is a vertical shrink of f of x by a factor of a if a is between 0 and 1. Here's an idea to think about how the points change through that transformation. If the point xy is on the original function, then the point x a times y is on the graph of a times the function. So in other words, the x does not change through this transformation, only the values of y are multiplied by that factor of a. So we can think of a vertical stretch as the graph gets skinny, that's a real mathematical term, isn't it? Or more vertical. And if the graph is a vertical shrink, we can say the graph gets, what, fatter? That's sometimes hard to see, but it really gets flatter, if you will, in this case. Flatter and fatter, huh? Who would have known? Now let's talk about what happens when we multiply the function by a on the inside. Okay, and remember what f of a times x means. That means you're replacing all the x's with that a times x. So you're changing the value of x before you really apply the function to it. So this is where we have an inside change, or a change to the value of x. Now, I've illustrated this again by a graph that's not one of the basic functions that we actually talked about in a couple sections ago, but it is a function if you have to take pre-calculus you're going to see. This is the sine curve, one of the trigonometric functions, but I think it does a really nice picture of showing the exact change when we have this factor of a that's multiplied by the value of x. So again, we have to break this up into two cases to see what happens when a is greater than 1 and when a is less than 1. So here's our original function. Doesn't really matter what those points are, but just to get a picture of how it's changing the graph. When we multiply the value of x by 2 on the inside, notice how that original function changed. So it changed it in a horizontal manner. And it actually compressed the graph, so to speak. In other words, if it's like an accordion, if you're on the end of that and you push it together, what's happening? Or a wire and you push it together, it compresses it. What happens if y is equal to f of 5 times x? Well, you see that effect even more, right? It's compressing it even further. And that's changing it horizontally. So in this one we say this is actually a horizontal shrink. It's bringing the graph together, you're pushing it together. And I have this on the next slide, but if you want to go ahead and note what I just said, is a horizontal shrink. Okay. Now what happens if a is between 0 and 1? So here's still our original function that we looked at just a moment ago, and I've entered on the calculator what happens if I input 1/2 x in place of x. Well, look what's happening now. It's still affecting it horizontally, but what's happening? It's almost like we're stretching that out in a horizontal direction. If I put in 1/10 of x, it's even stretching it out more, almost even to look like a line on that little window. Now, this is all in my standard window. Oh, you know what? It's actually not in the standard window. I just lied to you. This is on the z decimal window. But don't worry about the window really, but I just do want you to know that all the windows are the same. So as we're looking at the same piece of the graph, what's happening? It's like we're on the ends of that graph and just pulling it, stretching it in a horizontal direction. Okay? And so whenever we have a value of a that is less than 1, we get a horizontal stretch. Okay, so can you see the difference between horizontal and vertical stretch? If the value of a is on the outside of the function, we're affecting the y values, and that's stretching it in a vertical direction or shrinking it vertically. If value of a is on the inside of the function, then we're doing that in a horizontal direction. So kind of think about the accordion. So here's the conclusion. The graph of y is equal to f of a times x. Let me pause this. Okay, life interfered again, and I got a phone call. But what I was saying here is that the graph of y is equal to f of a times x is a horizontal shrink of y is equal to f of x if a is greater than 1. So horizontal shrink, think you're on the ends of the graph in the x-axis direction and you're pushing it together. A horizontal stretch of y is equal to f of x happens when a is between 0 and 1. So that's on the ends of the graph in the x direction, and you're pulling it apart. Now, what's really interesting here is how the x values are affected whenever we have a horizontal shrink or horizontal stretch. It's not quite as easy to understand the effect when the x values are changing. So I wanted to look at a couple of graphs here in both of the cases just so you can see what would happen through that transformation, because sometimes in your exercises you're actually going to have to identify the points that are on the transformed graph, so you need to know how to change those values. It was pretty easy when we had the vertical stretch or shrink because only the y values changed, the x values stayed the same, and the y values changed exactly in the way we thought. They were multiplied by that factor of a. Well, here I've looked at like the basic function square root of x, and then the transformation y is equal to the square root of 2 times x. Okay, so again, that's kind of like you're on the end of the graph and you're pushing it together. What's going to happen? Well, notice what happens here. So we're going to look at comparing points on the original graph to points on the transformed graph. So on the original graph, which is in my regular graphing font, if you will, and I've darkened the transformed graph, so this is that square root of 2x. Let's see what happens from that. So on my original graph, I have the point 0, 0, and I have the point 1, 1, and I have the point 4, 2. Now, let's look at what happens on that transformed graph. I still have the point 0, 0. What I'm looking for here is, remember how the x values are changing, the y values are not changing whenever we're doing an inside change. So what I want to look at is what value of x produces the same y values that I had to begin with. Well, so we know 1, 1 is here, but look at this. I'm looking for 2, 2. In fact, I can't really even see what's happening with my 1. That's why it just freaked me out just a minute ago. But 2, 2 is here. Okay. Originally on the first graph it was 4, 2. But notice that it is now 2, 2. So it took a value of 2 to get my original value of y. Well, how do 2 and 4 relate? 2 is 1/2 of 4, right? Okay, or 4 is twice 2. Okay, so whenever you're going through the transformation, I'm really not trying to make this more complicated than it looks. What you're really going to do here, if xy is on the original graph, then you're actually going to have to divide it by that value of a to get the point on the new graph. Okay? If we have square root of x and square root of 1/2 x, which is what that really is. Okay, let's look at this. So my original function is this original font, 0, 0, what is this, 1, 1, and 4, 2. Well, look, on the new graph, an x value of 2 gives me an output of 1. Because remember, we're stretching it in a horizontal direction, so it's going to take a larger value of x to produce the same result. Well, how do 1 and 2 relate? 2 is twice 1, right? But how did that really come about? If you use a rule here that you have to divide by that value of a, we take our original value, so if xy is on the original graph, and we divide it by the value of a to see what the new point is on the transformed graph, well, if we divide 1 by what is the value of a, in this case it's 1/2. And 1 divided by 1/2 is really 1 times 2, or 2. So it's kind of the opposite. It's just like when we had the horizontal shifts. Do you remember that? If we had a plus sign on the inside, we actually had to go to the left. If we had a minus sign on the inside, we had to go to the right. Well, here, if you're multiplying by value of a, you're actually going to have to divide the point by a to get the point that's on the transformed graph. So you're really using the opposite of what you think. Here we have a multiplication in our function, right? Our function is y is equal to f of a times x. But on the transformed graph, we're having to divide by a to figure out what that point on the transformed graph is. Okay?